The next talk with the title Emerging Heterogeneous Computing Architectures Every Software Engineer Should Know. uh, it's about compilers and DSLs, and the presenter is Babar Khan.
Hello. Oh, clear. Yeah, so it's still 11:15, so I'll say good morning, everyone. Thank you. I'll start with my topic, which is basically, I think, sorry, it's messed up. First slide. Okay. Yes, so one short question before I start. Does anyone know what FPGA is in this room? Oh, cool. That's nice. So even if someone does not know, it's fine. But so my topic is emerging heterogeneous computing architecture. Every software engineer should know. Basically, the crux of the topic is that at the end, I just want to give this idea that every software engineer should know the architecture, new architectures, because that's basically affects the performance benchmark and all that. So I'll start with the motivation. So two topics, two contents, basically what is the main motivation? So why is it now more important for a software engineer to know about the hardware? And exactly then I just basically build my case, one use case, which basically in my PhD, I have been working to target that problem, to bring that into an open source tool for software engineers. So motivation, so that's the goal. If you see, one report says in the US labor statistics that there are almost like 1.8 million software developers as compared to only 70,000 hardware engineers. That's basically the mismatch. We know now that the hardware is complex, and every engineer, whether you're a hardware or software engineer, you should understand the heterogeneous architectures underlying in your computer or anything which you use. Other thing is that in this Turing lecture, from the ACM Turing lecture, in which one of the computer researchers, David Patterson, mentioned that basically the next decades, next years, it will be all about domain-specific computing. So it does not matter if you are a software or hardware engineer, you need to understand your domain, and it's basically the next years, there will be more chips, so more underlying heterogeneous architecture. So that's the case that you should actually, as a software engineer, should basically know what actually the computer architecture you're using. The other thing is there's quantum computing. So that's basically, I'm not talking about the quantum computing, but that's what basically, I was in a conference last year in Denver, Colorado, basically supercomputer conference, in which basically it was all over, it was everywhere like quantum computing. So that's basically one more example that how the architectures will change in next years. So, and one basically goal was that one message was that there's a great need of people working on compilers. So the quantum computing, meaning that the physics problem is solved, but now you need computer engineers, software engineers, or people who are working as software hardware engineers to build compilers. So that's one more example that it's now more important to understand the hardware architecture. The other thing is that this was one paper in supercomputing, just one note, that's not my paper, but it shows that for only GPU programming model, you have different programming languages or programming models for each GPU vendor. So that itself explains the complexity of the heterogeneous architecture. This as well proves the case that if you're a software engineer, if you're a software developer, you should basically, you're dealing with a complex hardware, which is important to understand. So research on heterogeneous architecture. So basically, I have been working on some domain-specific languages and some compilers to target that complexity as a software engineer to build some tools that I can help the fellow software engineers to use that tool and not basically struggle with the hardware architecture. So that's basically, when I started my back years and master's thesis and PhD, I was working on some compilers. Basically, I was using C, C++, even C#, which is basically which is very rare if you're targeting an FPGA chip or ASIC chip. But this was an academic prototype, but we still proved that we can build compilers which basically can use C# programming languages to target complex chips. Other thing is that we contributed to a journal paper basically where we built a taxonomy of all DSLs and compilers being used since last 2 decades in academia about the ASIC and FPGA chips, all for the software engineers, all for the research software engineers who does not have that interest in hardware, but at some point they will have to use the hardware. So that's basically one contribution which we contributed. I mean, we did not, the taxonomy was the list of the compilers and DSLs which people can use as a software engineer. This was one research problem basically I have been solving in my PhD, which is still going on. Hopefully I'll finish it soon in next month. So I started with one problem statement that we do all use Linux operating system. That's obvious, Windows or. One problem statement was that we have an I/O stack in the Linux, and we have an I/O stack in the HPC I/O stack as well. So that's basically data center I/O, that's HPC I/O. We don't have to go into details, but the main idea was that this I/O stack is a bottleneck performance. It had a performance bottleneck. And how to basically accelerate that I/O stack, how to remove that I/O stack, we need to put that I/O stack some kind of an accelerator. So that's what basically, as a software engineer, I had basically to solve that case in the problem statement. So going deeper into the Linux block I/O, it's basically you have a multi-queuing part. It's basically an interface between the application and the storage. So going into the operating system stack as a software engineer to understand, okay, what kind of bottlenecks we can basically accelerate, abstract the programming language, and accelerate that on a special hardware chip. So we took a use case, basically, it's a Ceph distributed storage. It's an open source. Again, that was important that we take basically a use case that is open source. So we took a Ceph use case to actually put that in the Linux operating system, which is already, it's part of mainline Linux kernel, but we wanted to take an open source use case, which would basically help us to build our tool much for a better outreach of the users. So the research problem, further dissection is that first, that you have an operating system which has a block I/O layer, it has a performance bottleneck. Second, the same I/O layer has a code base which is basically very complex. So we decided to build a tool that actually solves both problem statements as a software engineer in an open source tool, and basically you're using a hardware chip underneath that tool. So we built a framework, basically it's called the Liba framework. It basically addresses both research problems. It uses the programming tools at the user space to tackle the complexity. And then it uses the FPGA accelerators. So that's basically the framework which I will show you in the next slide. So it looks complex, but it's very easy. So it's basically called development of Linux block I/O accelerators. So it's basically follows the 6 stages. There you have the application and the user space, like any user space application. Then you have a user space block I/O server, which is called NBD, network block device. Then you have a block layer libraries. If you see in the first 3 stages, even all 4, 5, everything happens at the user space part. So this basically, we build the programming tools that everything happens in the user space part. And here basically we involve the FPGA chip to accelerate the block I/O computations. Network library itself stayed at the user space part. As I mentioned that the Deliver framework has an FPGA chip. For some people who don't know what FPGA, but some of the people already know, but I have to put that slide. Basically, it's an IC chip, so that's basically the scientific word, but in reality, it's in more practical terms, it's something which basically it's an economical cheap hardware as compared to an ASIC chip. So you can basically rapidly prototype your solution on that. And it's basically massively parallel, so you are basically dealing with an architecture which is not CPU x86 based, so you can basically have a parallel computation on the FPGA chips. So that's in this case, either you have FPGA as a core processor, which is basically inside your server with the PCI interface, or you have a SoC chip, but in our framework, we were using this FPGA as a core processor, like in a simple host machine attached with the FPGA chip. So the programming model was based on C++ high-level synthesis. So that solves the case that, okay, high-level synthesis is basically not something new, but the thing is that how you build that programming language, a programming model, how you abstract that to how to program on the FPGA chips. So basically, the Deliver framework uses an I/O FPGA accelerator, which uses the high-level synthesis compiler underneath, a commercial high-level synthesis compiler. So we basically evaluated that on the data center FPGA chip. Basically, that's a considerable amount of FPGA fabric involved in that FPGA chip. So basically, we had 10 GB Ethernet server. That was enough for us. You can even go to 100 G, but in our use case, that was basically 10 G part. And it's the PCI base, so that's the evaluation for the hardware. We did improve the software part on the block I/O, so all that hardware part in this throughput, when I say software, that means that the Linux block I/O software part. And when I say hardware, that's basically the block I/O on the FPGA chip. So it's this is still the first use case. So we did achieve some speedups, but we tend to increase more in the next iteration of the framework. And that's the same case with the IOPS. We did increase some speedups. We did achieve some speedups on the FPGA chips as compared to Linux block I/O on the software part. So the conclusion was that the framework, the source tool, basically, which we have built, is giving some speedups on the FPGA chips. So it's an open source, so that's basically the main idea of my talk, that it should be accessible to use for the software engineers. And if you have a PR or anything, you can basically comment on that. And that's in detail, if you want to read about the complete framework, how to use that, what are the architecture details, it's all available there. Thank you very much.